Hello there. So in this lesson, we are going to start our introduction to trigonometry. Now, while trigonometry is the art of measuring angles, to get started with trigonometry and trigonometric questions, it's very important to have a clear understanding of the circle and the different lines we draw in and around the circle. So to start this lesson, we're just going to take a quick look at the circle. So here you can see we have a circle. So just to avoid any confusion, when I am talking about a circle, I'm talking about this line here, and every point on this line is the same distance from the center of the circle. When we talk about the circumference of a circle, what we mean is the length of this circle if you were to measure it. So if you were to cut this circle here with a scissors, and you were to lay it out along a ruler and measure the length, that is what we mean by their circumference. So I'll just clear that mark away. So one of the most important things about every circle is they have 360 degrees. And we usually denote degrees with this little circle here in the top right corner. So we have 360 degrees. And what this means in practical terms is that if you were to take the circumference of this circle and divide it up into 360 equal pieces, so we'll just put in the lines. So you can see here, all these lines have divided up the circumference of our circle into 360 equal pieces. The distance between any two consecutive lines here is what we call 1 degree. So I will just highlight a single degree. So you can see there we have our degree. Now if we were to zoom in on this degree, so this line here represents 1 degree. Now obviously this would have a slight curve in it, which I haven't represented here, but for illustration purposes, it's fine. Well, if we were to divide this degree up into 60 equal pieces, so we'll say like so, the distance between any two consecutive lines here is what we call a minute. And every degree has 60 minutes. So all a minute is it's like a finer measurement than a degree. And to denote a minute, we normally write the number 1 with an apostrophe. Okay, so a little mark on the top right shoulder. Now if we were to take one of these minutes and zoom in on it, so if we imagine this line down here represents 1 minute, then if we were to divide this line up into 60 further equal pieces, like so, the distance between each two consecutive lines here represent what are called second minutes. Or seconds, as you would be used to referring to them. So 1 minute has 60 second minutes or seconds. Now you could take one of these seconds, zoom in on it, divide it up into 60, take one of those, zoom in, and carry on ad infinitum, depending on how accurate you need your measurements to be. But for what we are doing, we will just use degrees, minutes, and seconds. And to denote a second, we put the number 1 and we put 2 marks on the top right corner, or 2 apostrophes. So now you have a visual idea of what we mean by a circle and when we talk about degrees, minutes, and seconds. So what we wish to do now is take a look at an angle. So when we talk about the measure of an angle, or we refer to an angle, what we are talking about is how much of the arc of a circle is contained between the two sides or the arms of the angle. So to illustrate this, we have our circle here again, and you can see we have marked an angle on this circle. Now this is an angle of 40 degrees. Okay, and we know what this means. So if I just put in the degree lines around this circle, so we can see that between the two arms of our angle there are 40 degrees of the circumference of a circle. So if we just focus on this angle here for a moment, these two lines which make up our angle are called the arms or the sides of our angle. And this point here where they meet, this is called the vertex. And we'll label this vertex A. And what we would say is that A is an angle of 40 degrees, or that the angle A subtends an arc of 40 degrees. And what this is telling us is that our angle A has two rays, or the two sides of our angle, pass through the endpoints of an arc, and the arc is 40 degrees, or 40 of the 360 equal parts of the circumference of a circle. Okay? Now the side where the angle starts, this is called the initial line. And the side where our angle ends is called the terminal line. So you may be wondering, how can we tell which line is the initial line and which line is the terminal line? Okay, so to answer this question, I'm going to clear away this angle and just put our circle on the coordinate axes. So here we have our circle. This here is the x-axis. And of course up here we have the y-axis. This is the positive side of the x-axis. This is the negative side. This is the positive side of the y-axis, and this is the negative side. Now by convention, the angle of 0 degrees lies along the positive side of the x-axis. Okay, so this angle here is 0 degrees. And what that means is that our initial line and our terminal line are both lying along the positive of the x-axis. Because they lie along the positive of the x-axis, they don't have any part of the circle between them, so the angle is 0 degrees. Okay, and we can illustrate that by putting in the degree lines again. So here we can see that the initial line and the terminal line lie atop of each other along the x-axis, the positive x-axis, and since they don't have any part of the circumference of the circle between them, then the angle is 0 degrees. Now the initial line doesn't move, but the terminal line rotates around a fixed point, and that fixed point is what we call the vertex of our angle. So for our angle of 40 degrees, the terminal line is going to start rotating up this direction until it contains 40 degrees. And then you will have your angle of 40 degrees, like so. Okay, so our terminal line has rotated around the vertex 40 degrees. So this is our 40 degree angle. And that is our angle. Now you could well argue that we could have gone this way as well and also measured 40 degrees, which is true. And here we have another angle, which is also of 40 degrees. But there is a convention to avoid such confusion, and the convention is as follows. If you are measuring an angle, unless you are told otherwise or have reason to do otherwise, all angles are measured from the 0 degree mark. And if we measure an angle anti-clockwise, this is a positive angle. If we measure an angle going clockwise, then it is a negative angle. So this angle here is actually minus 40 degrees, while this angle here is plus 40 degrees. Okay, so that's very important, that convention. So this line is still a terminal line, and our initial line still lies here at the point 0. But if we start going clockwise, it's a negative angle, and if we start going anti-clockwise, it's a positive angle. Okay, so there's just one or two further points I would like to make. Now we know every circle has 360 degrees, and you can see here that our coordinate axes divide the circle up into 4 quadrants. Each of these quadrants contains 90 degrees, or 1/4 of the 360 degrees in the circle. When we have an angle that is less than 90 degrees, so this angle here of 40 degrees, the number of degrees we need to add to this angle to make it a 90-degree angle is called the complement of the angle, okay? So the complement of this angle here of 40 degrees would have 50 degrees. So that angle of 50 degrees is the complement to this angle of 40 degrees, because it's how many we need to make up 90 degrees. Also, the number of degrees we need to add to a given angle to make it equal to 180 degrees. And you can see here that half of any circle has 180 degrees, or 2 right angles. And the number of degrees we need to add is called the supplement, okay? So the supplement of this angle of 40 degrees is the number of degrees here, which we would need to add to 40 to make 180. So in this case, it's 140 degrees. So 140 degrees is the supplement, and 50 degrees is the complement of the angle of 40 degrees. So that's our recap of a circle and an angle. So what we wish to do now is to go and take a look at some of the lines which we draw around the circle, and these lines give us what we know as the trigonometric functions, so your sine, cosine, tangent, and so on. And once we have identified these trigonometric functions, what we'll do is we'll take a look at some of the relations we can derive between them, and that will set us up nicely in the next lesson to start making use of this information to solve right-angled triangles. So, to take a look at the trigonometric lines, we have here our circle, and our circle again is centered on the coordinate plane. So this point here is the origin, and we'll just mark the 4 points where our circle intersects the x and y axes. So we have these 4 points here. So just to be clear, we have the y-axis here, and we have the x-axis over here. Again, we have the positive y-axis, negative y-axis, positive x-axis, and negative x-axis. So, to give these letters, we'll label the origin O, as is always the case. This point up here we will label A, and down here we will mark B. We will mark this point C, and this point D. Now the lines AB and CD, these are diameter lines, and a diameter line is a line whose endpoints lie on the circle and which passes through the center of the circle, okay? And the lines OD, OA, OC, and OB are all what we call radius lines. So they are semi-diameter or radius length lines. Now, you can any line that comes from the center of the circle and ends on the circle is a radius line. So I'll just add in another radius length line. So this line here, which we have just added, this is also a radius length line. And if I mark this point E, so what I'm going to do now is draw another line from the point E to the other end of the circle down here, and this line will be perpendicular to the line OD. So I'll just draw that line now. So I'll just highlight a few points. We have the point E here. We have this point of intersection, and we have this point down here. Now, if we label this point F, EF is a chord of our circle. So any line whose two endpoints lie on the circle is a chord, and it follows that the diameter is a chord, but it's a special type of chord in that it passes through the center of our circle, and it is also the longest possible chord you can have on a circle. So any line whose two endpoints lie on the circle is a chord of the circle. The longest possible chord is a diameter, and a diameter is a special chord because we know that if it's a diameter line, it must pass through the center of our circle. Now, if we label this point here, the point G, and this line is perpendicular to OD, so this is a right-angled line here, okay? So EGD is a right angle. This line EG is what we call the sine of an angle. So if we take our angle, and I'll write it over here, if we take the angle DOE, and I'll just mark this angle here as theta. So the sine of the angle DOE, or the sine of theta, is equal to this line EG. That is what we mean by the sine of an angle. So this angle DOE refers to the arc ED, okay? We know that this measures the number of degrees in the arc ED, and so the sine, which is this line here, is the line, one point of which touches one end point of the arc, and the other point of which is perpendicular to the diameter line passing through the other end point of the same arc, okay? So our arc ED, one end point is touched by one end of our sine. The other end of sine touches the diameter line CD, which in turn touches the other endpoint of the arc ED. But the length of this line, EG, that is what we mean when we say sine. Now, as we have previously said, the complement of this angle theta is the number of degrees we need to add to it to make 90 degrees. So this angle here, which we will call alpha, is the complement of theta. And what we will do now is draw a line from the point E perpendicular to the diameter line AB. Okay, so I'll draw that line now. And I'll just mark this point here. So if we call this point H, then EH will be the sine of alpha, but since alpha is the complement of theta, EH is the sine of the complement of theta, or the cosine, so the complement sine of theta. So the sine of the complement angle of theta is equal to EH. Now, this here is a right angle, and this here is a right angle. We know that our coordinate axes are at right angles, and because of that we have a rectangle, and because we have a rectangle we know the length HE is going to be equal to the length OG, which means that this length OG is equal to the cosine of theta. Because EH is the sine of alpha, which is the complement of theta, so cosine is the sine of the complement angle, and because we have a rectangle, this length is equal to the cosine of theta. So that's sine and cosine. What we are going to look at now is the tangent and the secant. And I'm going to draw these two lines at the same time. So we'll add those lines now. So I've added another point here. We'll call this point I. So the line DI is what we call the tangent. And the line OI is called the secant. So I don't want to try and write secant in here because it'll get too congested. So I'm just going to say here OI is the secant. So the tangent line is the line that touches one endpoint of our angle. So here we have our angle DOE, and one endpoint of this arc ED is touched by the tangent line OI, and we have the other arm of our angle OE produced until it intersects the tangent line is called the secant line. So this line OI is the secant, and this line DI is called the tangent. Finally, we're going to add one more line, and you can probably already guess it's going to be the tangent line through this point A. So I'll add that line now. And I'll just mark this point here. So if we call this point J, then the line AJ is the tangent line of the angle alpha. Okay? So we call this the tangent line of alpha. And again, because I don't want to clutter this up too much, I will just write over here that OJ is the secant of the angle alpha. So we have the tangent of alpha is equal to AJ, and that is the tangent of the complement of theta, or the cotangent of theta. And using the very same argument, we have that the secant of alpha is equal to OJ, and that is the secant of the complement of theta or the cosecant of theta. So there are just two more lines I wish to highlight. We have the line GD, which I will write over here, and this line is called the versed sine of theta, and you don't get any prizes for guessing that AH is the versed sine of alpha which is equal to the coversed sine of theta. Okay, so there are our trigonometric lines. Now you can see that if we change this angle theta, the lengths of all of these lines are going to change. So all these lines are functions of the given angle, and so they are the trigonometric functions. And what we wish to do now is to focus on this top right quadrant, and there are three triangles in particular which we wish to pay attention to. So I'm just going to set up those triangles now, and we'll see how they are taken from this top right quadrant, and using those triangles we are going to work out some relations between our trigonometric functions. So here we have the top right hand quadrant of our previous diagram, and I've tried to fit in as much information as possible without making it too congested. And what we are looking for is three triangles in this, which we will match up along here, and these three triangles are similar triangles, okay? And we're going to use these triangles to find some important relationships between the different trigonometric lines. So, because this angle here is a right angle, and this angle here is a right angle, this angle in here is the same size as this angle up here. And this is all coming from the properties of similar triangles. Now, this angle here is also a right angle, and because this line OD is parallel to the line AI, this angle in here is also equal to the angle theta. Because of that, this angle down here is the same as these two angles. So you can see now we have identified three similar triangles, and I'm just going to line those triangles out here. So in all of these triangles, this angle down here will be theta. And if we write in the sides of these triangles, if we put this base here as cosine, then looking here, the right angle on cosine is sine. And the hypotenuse of this right angle triangle has a length which is the radius length. So this will be the radius. If we take the bigger triangle here, the larger triangle, OD will be radius length, So we'll make that this one here. The perpendicular will be the tangent. And the hypotenuse here will be the secant line. Finally, if we look at this triangle over here, OAI, this angle, theta, the base will be the cotangent, which will be this one here. The hypotenuse will be the cosecant. And the perpendicular will be radius length. So I'm just going to put the letters on these corner points to help you identify them against the diagram here. So what we want to do now is look at these triangles. And these are similar triangles, so the ratios of their sides will be equal. So straight away, from this triangle, using Pythagoras' theorem, we can say that sine squared theta plus cosine squared theta, and SIN is just short for SINE, and COS is short for COSINE, and they are equal to the radius squared, where I've put or here for radius. And we also can see here that if we have the radius squared plus tan squared theta, where tan is short for tangent, that is equal to sec squared theta. And again, this is just short for secant. And in this final triangle over here, we can see that the radius squared plus the cotangent squared, where COT is short for cotangent, that is equal to the cosecant squared. Okay? Now, because all of these relations are true for a circle of any radius whatsoever, if we set the radius equal to 1, then we get sine squared theta plus cosine squared theta is equal to 1. This relationship gives us 1 plus tan squared theta is equal to sec squared theta, and this relationship gives us 1 plus cotan squared theta is equal to cosec squared theta. Now the unit circle is very, very important for what we are doing, and we will come on to that soon enough. What I wish to do first is just highlight one or two other relations we can work out with these triangles. So, still making use of the fact that these are all similar triangles, we can say that sine of theta to cosine of theta will have the same ratio as the tan of theta to the radius. And if we have a unit circle of radius 1, then sine of theta to cosine of theta will just be equal to tan of theta over 1, which is just tan of theta. We can say that the cosine of theta to the sine of theta will have the same ratio as the cotangent to the radius. Again, if we are dealing with a unit circle, Then we have cosine of theta over sine of theta is equal to cotan of theta over 1, and that is equal to cotan of theta. So the final thing I wish to show you from just these simple triangles is that we can express any of these lines, sine, cosine, and so on, in terms of any one of the lines. So what I am going to do is show you how you can express the cosine, tangent, cotangent, secant, and cosecant in terms of the sine only. So we'll do that now. So we're going to work all of these from a circle of radius 1. Now we have shown that sine squared theta plus cosine squared theta is equal to 1. And that would give us that cosine of theta would be equal to the square root of 1 minus sine squared theta. We know that tan of theta is equal to sine of theta divided by the cosine of theta, and that is equal to sine of theta divided by the square root of 1 minus sine squared theta. We also know that the cotangent of theta is equal to cosine of theta divided by the sine of theta, which is equal to the square root of 1 minus sine squared theta divided by sine theta. We can see that the cosecant will be to a radius of 1. So we can say cosec theta over 1 will be equal to, and the radius over the sine, so that will be 1 over sine theta. And finally, we can see that the secant to the radius, so sec theta over a radius of 1, would be equal to the radius over cosine, so 1 over cosine theta, which would be equal to 1 over the square root of 1 minus sine squared theta. Okay, so you can see that we have expressed the cosine, tangent, cotangent, cosecant, and secant only in terms of the sine. And you can do this with any of the trigonometric lines you so wish, and it's something that's worth practicing. So we're going to stop this lesson here. We have covered quite a lot of the fundamental ideas of trigonometry, and I've tried as far as possible to show it to you from a geometric point of view, so you can kind of visualize that cosine, sine, tangent, they aren't just abstract ideas, they have a solid foundation. I would strongly advise you to try and memorize this top right quadrant diagram, and to be able to reconstruct it. And we're going to make a lot of use of this in our next lesson when we go on to solve right-angled triangles.